Okay, so I think I'm set up here. So on 10.3, what we're going to do is we're going to talk about what it means for a function to be continuous, and what it means for something to be discontinuous, okay? So here's kind of the situations that we're looking at. If you look at this particular function on this example right here, so you have a line, f of x equals x plus 2. It's got a y-intercept of 2, and it's got a slope of 1. Okay, so what's happening on this is if I wanted you to say what is the limit as x approaches 2, okay, if you're going to 2 from the left and the right, where is that limit going? It's going to 4. Okay, and then if I ask for this, if I say f of 2, what am I asking for if I say what is f of 2? I'm asking for the y value when x is 2, right? Okay, so this just means, this statement right there means if x is 2, if you look at your graph, y is also equal to 4. So what it means for something to be continuous is it means there's no break in the graph. No break whatsoever. Okay, sometimes graphs have breaks, and we've seen that. So this one is continuous at x equals 2. Okay, and that's part of the reason we're going to talk about is the function is defined. Okay, that's what f of 2 equals 4 is, and then the limit has the same value. The fact that those two numbers are the same is what makes it continuous. Okay, so look at the next one. Now we're looking at this function. Okay, tell me where this thing's undefined in your head. That 2. Remember we talked about this too, so you might want to write a little note like this. You can factor that numerator as x plus 2, x minus 2 over x minus 2. Okay, what did I say happens if something cancels out? What does that mean on a graph? It's a hole. Okay, so that's a hole. So what happens on this one, if you did the limit, okay, if you just kind of look at that left-hand limit and that right-hand limit, that's going to go to 4. But the thing is, the function is not defined. So what that means is it's not continuous. So that one is not continuous at x equals 2. There's a break. Okay, the simplest way to get this is, okay, there's a break in the graph, it's not continuous. Okay, and then the last one goes like this. Basically, if you did the limit, the right-hand limit and the left-hand limit are going to go to different values, so that limit's not going to exist. And the function's not defined either, so that would also not be continuous at x equals 0. Okay, now for this class we won't get too technical, but one of the things I want you to be able to do is if you have a graph, it's very simple to identify where something's discontinuous and where it's continuous. Okay, and then we'll start getting into the definition. I want to help you understand the definition. Okay, let's take this graph right here, and what we're going to do is figure out where it's discontinuous. So all you're doing is looking at a break in the graph. So in other words, if you were drawing this graph, you would actually have to lift your pencil at -2, right? You'd draw a bubble, then you'd lift your pencil. Therefore, it's discontinuous. Another place it's discontinuous is -1. If you're going to draw that graph, you'd have to lift your pencil, correct? Okay. Same thing here. If you were going to draw this graph here, you would have to go there, lift your pencil, and then draw it there. So you're also discontinuous at 1. So any place you have a break where the graph's not nice and smooth, then it's discontinuous. So we're going to say this is discontinuous at -2, -1, and 1 like that. Okay, that's all we mean by a graph being discontinuous. There's a break. Okay, now if I want you to tell me where it's continuous, then you have to do intervals. Okay, so this is interval notation. So what I'm going to do is kind of highlight this right there. It would be continuous from -∞ until you get to -2, and then you would have to have a parenthesis there. And the reason you'd have that parenthesis is because that you don't want to include the -2. Okay, so you're nice and smooth. Okay, the next place you're continuous is from where to where? -2 to -1. Nice and smooth in there. So that's the next place. So I'll just kind of highlight that. And generally you just write this like this. Union -2, -1 with parentheses. You don't want brackets because that would be including that. Okay, where's the next place? -1 to 1, right? Then you got a problem at 1. So you're now going to go -1 to 1. Remember, you're doing intervals with x values. Okay, so our next thing is we just say union -1 to 1. Okay, and then where's the last place? From here on out, right? Okay, so what you would say is we're continuous from 1 and then forever. Okay, so that would be how you would write that interval of continuity. Okay, now these things right here are all x values. So you're just saying from -2 to -2, -2 to -1, -1 to 1, and so forth like that. Does that make sense to everybody?
Do you
Yes.
put brackets around the infinity ones?
No, you never put brackets on infinity because it wouldn't make any sense. Anytime you put brackets on something, you're telling me that it's included and it's really a definite endpoint. There's no endpoint to infinity, so we always have parentheses around that. Okay? All right, does that make sense to everybody what I'm doing? Okay, is everybody okay with writing intervals? Okay, that's another little background issue that sometimes students get into here. Okay? Okay, so here's kind of an example. I took some stuff out of the book because the book's got several good examples. So in applications, some functions are continuous, some are discontinuous. A good example would be this right here. If you were looking at like a temperature for a 24-hour period, that's always continuous. And the reason is because at any point in time, you could measure the temperature, right? There's no point in time where you said, oh, the temperature is undefined, right? Okay, so that's continuous. Here's a business application. This one's clearly discontinuous. This says your inventory in your warehouse. How much you have for a product in a warehouse is going to change, isn't it? It's going to fluctuate. At least you hope that you're selling stuff and you're bringing more stuff in, right? Okay, so that one's discontinuous because it changes from week to week. Does that make sense? Okay, so some applications lend themselves to something that's continuous, some's discontinuous. Actually, economics, most of the time, you got stuff that's discontinuous at different places because that's the way things change, okay? Now, the next thing is, this is sometimes the hardest part for students to learn, but we want to try to get clear on the definitions. One of the hallmarks of math is you can very, very carefully and precisely define stuff, okay? So we don't say that, well, discontinuous is a break in the graph. That's not very mathematical, that's just sort of an idea, but we can define it this way. So I'm going to try to help you understand this definition. So it says, first of all, in order to be continuous at a point, these three conditions always have to hold. Okay, the limit has to exist. Okay, the function has to exist. You can't have like a place where it's undefined. And then this is the thing you're going to wrap your head around, is the value of that limit is the same as the function value. So I'm going to take you through some examples and kind of show you how this definition works, okay? So let's look at this first one right here. All right, does everybody agree that we are discontinuous at x equals 3? Because there is a break in the graph. Well, let's see why with the definition. Okay, tell me if this is true or not. Is f of 3, is that defined? Is the function defined? Absolutely, there's a solid dot right there. So that just means you have a point like 3, 1. So yes, that's cool. Okay, how about the limit? If we're doing the limit as x goes to 3, does that exist? No, that's why it's discontinuous. That's what fails. Okay, so that's why. Okay, now the same thing here. This is not true either, because what is the value of f of 3? F of 3 appears to be about 1, right? The limit doesn't exist anyway, so that doesn't hold anyway. So if any of these three conditions fail, then you're discontinuous. Tell me if that makes sense. If the limit doesn't exist, you're discontinuous, guaranteed. Okay, all right? Let's look at the next one. Okay, second graph. Tell me if f of 2 is defined or not.
Yes.
Yes, okay, there's a solid dot. What is the value of f of 2? What's the y value when x is 2? 1, okay. So yeah, okay, we're cool there. Okay, how about the limit? Does this limit exist?
Yes.
Yep, okay, what's the value of that limit? 4, okay, right? Okay, so it does exist. Even though there's a bubble there, it doesn't matter. The thing is, if you're going from the left, you're hitting 4. If you're coming from the right, you're also hitting 4. So that limit is equal to 4, okay? All right, now here's the thing, the clincher on this. Okay, we said, what did we say the value of that limit was?
4.
4. What did we say f of 2 is? 1. Are they the same? No. That's why it's discontinuous. Okay? If they were the same, then they'd be continuous. Okay? Because basically, if they were the same, that solid dot would fill in that bubble. Does that make any sense? Okay? Tell me. I have no idea. Okay? All right? Let's look at this last one here. This one's pretty simple. Tell me, is this function defined at 2? No. So it's discontinuous just for that reason. Okay? Does the limit exist?
Yes.
Yep, it exists. Okay? But the thing on this one, this would not be true because that limit is going to be 6. But that thing right there is not even defined anyway. So the only way something can be continuous is if all 3 of those things hold. Okay, that's the abstract theoretical part of that. You want to try to wrap your head around that definition. Okay? Okay, let me see if you guys understand what I just was talking about. Okay, I'm going to give you this graph, and I'm going to let you give you a few minutes to see if you can figure this out. Okay, there are, how many places on that graph do you see like breaks?
5. I say 7. 6.
Hold on, be careful. Just look at x values, okay? Only x values. Is there a break there?
4.
Yeah. Is there a break there?
Yeah.
Yeah. Is there a break there?
Yeah.
Is there a break there?
Yeah.
Okay, when you're saying 7, you're looking at all the little dots and everything. I want you to look at x values. So there's 4 places that you're discontinuous. So what I want you to do is identify those places. Then I want you to tell me at least one reason why it's discontinuous. Your choices are functions undefined, okay? Second choice would be limit doesn't exist. Third choice would be the one, that's the one students have trouble with sometimes, is the value of that limit has to be the same as the function value. Try it out and see what you think. See if you can kind of wrap your head around that. Now you could have more than one reason why they're discontinuous. Just try to identify any reason that it's not discontinuous, that it's discontinuous, okay? Reason, okay? All right, well, what's the first place it's discontinuous?
-4.
-4. What's the reason why? Is the function defined? Yeah, it's defined. There's a solid dot there, so it's not that. The limit doesn't exist, does it? Okay, that's one reason, okay, is number 2 is the limit doesn't exist. That's reason number 1. Now, what would be the, this one doesn't hold either because the limit doesn't exist. But really, the fundamental reason is the limit doesn't exist. Okay, does that make sense? Mm-hmm. Okay, all right. What's the second place it's discontinuous? Okay, what's the reason?
It's undefined.
It's undefined, exactly. See, there's a hole there. There's not a solid dot there, so that would just be it's undefined. That's reason number 1. That's good enough. Okay, what's the next place? What's a reason?
It doesn't equal 30.
Okay, but it's also, it's undefined, right? Okay, then you got 2 open bubbles, so that would be 1. Does the limit exist? No, the limit doesn't exist either. That's another reason. And therefore, 3 wouldn't hold either. I mean, 3 is not going to hold unless the limit exists.
So basically, the third one is what the function equals is not the limit.
Exactly.
Okay.
Yeah, that would be like the kind of what's the next situation? It's kind of like you have a limit that exists like this, right? But the value of that limit would not be the same as the function.
Right. And the first one, -4, the third rule wouldn't apply because the function is defined.
Well, the limit doesn't exist anyway.
Okay.
Okay, I mean, yeah, this really would not apply. On the first one, 3 doesn't apply either. Okay, and the thing is, if the limit doesn't exist, then 3 is not going to apply anyway. It can't, okay, because the limit has to exist. Okay, where's the last place? 3? Is that right? Okay, so what's the reason?
Function doesn't equal the limit.
Right, now see, this one, you are defined, right? The limit exists, right? Okay, so that's good, but what fails is 3. Okay, see, the idea with this one is the limit as x goes to 3 is going to be equal to 1, 2, 3, isn't it, right? Okay? Okay, what's the value of this function? 1, so it's not equal to that. All right, does that make sense? That's the hardest one for students. All it's saying is whatever that limit value is, it has to be the same as that function value. If it is, then you're good. Okay, so that's what it means for something to be continuous. Okay? All right, students never have any trouble at all identifying where the discontinuities are, but sometimes don't understand the technical part of the why. Okay, now next thing we want to look at is that some of this is just going to be some review. So a linear function, so you want to write down these forms. A linear function, and we've already reviewed this quite a bit, it's just mx plus b, y equals mx plus b, okay? So a linear function, if you graph a line, is it going to have like a hole or a break anywhere? No, okay? So it's continuous everywhere, and if it's continuous everywhere, we say it's from negative infinity to infinity. Lines do not have breaks in them, okay? All right, a rational function we've talked about looks like this, okay? It's basically just a ratio of polynomials. You could have a polynomial on top and a polynomial on bottom. That's what rational functions look like, okay? So what would be a problem area on a fraction? Where the denominator is 0, right? So it's going to turn out that you're going to be continuous everywhere except where that denominator is 0, because you'll either have a vertical asymptote or what's the other possibility? A hole. And that's it. So basically a rational function is continuous everywhere except where the denominator is 0. And that's going to be an asymptote or a hole. Okay? A square root function typically is going to look something like f of x. We're just going to have kind of the basic one like that. Now it can be the square root of something. Okay? Now that x can be any kind of expression. So basically, when you have a square root, what kind of number has to be under the square root? Positive. But there's one other possibility. It can also be 0, can't it? But what it can't be is what? A negative. Okay? So what's going to be on this? A square root function is going to be continuous where the number under the radical is greater than or equal to 0. So it can be 0 or it can be positive. You just know that you can't have negative numbers under a square root. Okay? And then a root that's odd. Okay, let's say like you have a cube root of x. Sometimes students don't understand this one as well as I'd like. Okay, can you do a third root of a negative number? Is that okay? Yeah, it's cool. Okay, like if you have the negative cube root of negative 8, that's negative 2, right? Okay, can you do a cube root of 0? Of course. Can you do a cube root of a positive number? Yeah, okay, so it's everywhere. So cube roots are always going to be continuous, and so would a fifth root, a seventh root, and so forth, okay? So that's going to be continuous from negative infinity to negative infinity. It's only the even roots that you can't have negative numbers on. Okay, does that make sense? Okay, all right, so what we're going to do with this, partially we're just trying to get comfortable with functions, with a variety of functions, because you see these in applications quite a bit. So if you have this, if you graphed y equals 4 again, what does that look like? We call that a constant function. It's actually a line, but the type of function that is, we usually just call that a constant function. Is there going to be any breaks in that graph? No. Okay, so you're going to have, that's going to be continuous everywhere, so we just say negative infinity to infinity. Okay, what kind of function is the next one? That's linear. Are there any breaks on a linear function? No, so where's it continuous? Everywhere. Okay, so you know that. So you want to know, okay, I got a line, it's always continuous. Okay, all right, the next one, what kind of function is this one? Rational. Okay, is there any place where this thing might possibly be discontinuous? You can probably do this one in your head, 2 and negative 2, right? Okay. But what's happening is if you factored this, and you don't have to do that, you can do this in your head if you want to, you would get x plus 2, x minus 2, right? So there would be actually 2 vertical asymptotes. There wouldn't be any holes because nothing crosses out. So what we'd have to say on this is we'd say discontinuous at x equals negative 2 and 2. You could even just say discontinuous at plus or minus 2 if you want to. And then continuous would go like this. It's everywhere except those two numbers. So you'd have to go like this, negative infinity to negative 2, right? Then from where to where? Negative 2 to 2. And then from where to where? 2 and forever. Okay, like that. So you got to break that up into intervals like that. And yeah, you got to use parentheses around everything. Okay, that excludes those. Okay, that's how you know that. So those are the only two places that function is going to be undefined and discontinuous. The next one's also a rational function. Okay, so we need to figure out, look at the denominator and see if you can figure out what makes the function undefined. So what do you need to do with the denominator probably? You need to factor it, okay? So let's go ahead and factor that. So you're going to have x and x to get x squared, okay? What should I use for 10?
1 and 10.
1 and 10, good. Okay, if you're going to get a 9 out of a 10, how do they got to add up?
X plus 10.
X plus 10, x minus 1, good. Okay, is that enough for you to tell me where it's discontinuous?
And 1.
Negative 10 and 1, right? Okay, so we're going to be discontinuous at x equals negative 10 and x equals 1. Everybody with me there with the factoring and how I did that? Okay, and if you're a little rusty on your factoring, you need to get that settled. But again, that's just 10x minus x gives you the 9x. Okay, yes?
So since the x minus 1 cancels out, it's still...
It's still, now the thing is that it still is discontinuous there because there's a hole. See, this one would be the vertical asymptote. Oh, hold on, is this something? Oh, I'm looking at the wrong problem, sorry, okay? Yeah, this one would be the vertical asymptote. That would be a hole, so it's still discontinuous, okay, for that reason, okay? Then we'd say continuous, we'd say negative infinity to negative 10, right? And then where?
Negative 10 to 1.
Negative 10 to 1, and then where?
1 to infinity.
That's it, okay? That's how you write it, okay? So if you have knowledge of how rational functions work, you can figure this out without having to look at graphs, okay? That's what I want you to be able to do. Okay, this one is a square root function. And when you have a square root function, okay, what kind of number has to be underneath that radical? 0 or positive, right? So the way you can do this is it's sometimes a little hard to do this in your head. So what you do is you just write down that thing. We call that the discriminant. You don't have to know that term. But you take that and set it greater than 0. Greater than or equal to 0. Then if you solve that inequality, it'll tell you where it's continuous, okay? So if you solve this inequality, what do you need to do? Just like solving an equation. You add 3. You're going to get 2x greater than 3. Then you're going to divide by 2. So you end up with x greater than or equal to 3 halves. So as long as your 3 halves are bigger, then you're going to have a graph, okay? You aren't going to have anything below 3 halves. So the way to write this would be in an interval. This time you would say bracket. Why would you put a bracket? Because of the equal to, right? So you'd say 3 halves, infinity like that, okay? So that would be how you write your result like that, okay? And if you did this, I'm going to show you real quick just on a calculator. You don't need to do this necessarily, but you know, anytime you're in doubt on things like this, your graphing calculator will open you up to this. So if I just put in square root, and let's see, then I'd put in 2x minus 3, and I'm going to do a standard window here, so I'm going to go zoom 6. Okay, here's what would happen. Notice that your graph, where does your graph start? 3 halves. 3 halves is 1.5, right? So from 1.5 on, you got a graph. Everywhere else, you got nothing, right? So that's how that works out, okay? All right, everybody understand that okay? Okay, the next one's the one that I think you could run into some issues on this if you weren't careful. Okay, this one again is a square root function. Okay, this one you can tell pretty easily on a graphing calculator, but what you have to do on this problem is do exactly the same thing you did on the last problem. Whatever's under that square root has to be greater than or equal to 0. Okay, it has to be. Now, what I'm going to do is I'm going to show you how to reason this out graphically. Okay, what would that function look like? That is a polynomial. It's got an even degree. That number is positive. What would that look like? Like that. what is that minus 9? What is the significance? Like down 9 or a y-intercept, right? Let's just do this. Okay, let's go through and just put a dot there and maybe locate that as that's 0, -9. We know the graph is going to do this. We know that for a fact. Okay, the other thing is you can factor this and get x plus 3, x minus 3. Okay, now what's going to happen on this is if you take this and set this equal to 0, that gives you what's called an x-intercept. Okay, so what would be, if you solved this equation, what are the two x-intercepts just in your head? -3 and 3. Okay, so you get x equals -3 and x equals 3. Okay, and that's real important that you get those intercepts like that. The way that you always find x-intercepts is you set this equal to 0. And that has to be solved by factoring. Okay, and then the way you find a y-intercept is just replace the x with 0. Okay, so what you have, you'd have a graph that looks like this. So here's what we're doing with this to figure this out. Is we're interested in where the y values are positive. On this graph, where are the y values positive? There, right? And where else? There. Okay, and that's going to give us a way to write our answer. So it's going to look like this. You're going to have positive numbers there, but what you're going to run into problem with here is you're going to have a bunch of negative values right there. And you can't have that under the radical. So what you would say is you would say this graph is continuous from -∞ to -3, and then you bracket it, because it's okay, because if it's -3, then it's the square root of 0, and then it would be union, and then from where to where? 3 on. Okay, like that. So it's 3 to infinity like that. Okay? And then it would be discontinuous in that kind of region in the middle. So we'd say this is discontinuous from, and that would be -3 to 3 like that.
Would you bracket it?
No. Okay? And the reason is because, remember, you're doing a square root. If x is equal to 3, isn't that just the square root of 0? Which is okay, right? It's okay if x is -3, and it's okay if it's 3, but it's not okay if it's anything between -3 and 3. Does that make sense?
So the parentheses is just saying anything a little bit less than.
Exactly.
Okay.
Yeah, like 2.999 forever.
Right.
Like that, okay? Now,
If it was -3, it would equal 0, which means it would be.
you would end up with a square root of 0, which is okay.
Okay, right.
Okay? All right, so here's what we really did. So once you put this in your calculator, I'm going to take off this. Just do this along with me here. Actually, what we just got through doing was we reasoned out the answer to this problem without a graphing calculator. But now put it in like this. Just go to y equals and put in square root, and then put in x squared minus 9. Okay, see the graph I did right here is not the graph of the square root. It's the graph of x squared minus 9. And if you do like a zoom 6, let's see if this makes any sense to us. Okay, well, here's what the deal is. We're nice and continuous from there to there, right? We're continuous from 3 to infinity. What's the deal there? There's not even a graph there, so we're not continuous. You've got to have a graph there before something can be continuous. Okay, so when you do this with your graphing calculator, you can make a lot of sense out of this, but you want to understand the mathematics so that you can figure that out without having to just look at your technology over and over again. Does that make any sense? Okay, all right. Okay, let's do these last couple here, and then just a few other things. We want to move on here. Okay, what kind of function is the next one? It's a polynomial, right? Okay. Can you tell me which dance move this polynomial would be dancing to? It'd be doing this thing, okay? Does that have any breaks in it? No, polynomials are smooth. They always are. The dancers are smooth. Okay, there's no breaks anywhere in that, so that's continuous everywhere. That's a guarantee. If you have a polynomial, it's continuous everywhere. Okay? Now the next one is a cube root function. Okay? Now, what you want to reason out on this is a cube root can be negative, right? You can do a cube root of a negative. You can do a cube root of 0. In fact, you can do a cube root of anything. So is there any breaks in this graph? No. So this one is also continuous everywhere, okay? Let me show you how to do a cube root on a calculator if you don't know that. So on a TI, typically, if you look at your math button, you know, the math button typically will have a cube root like in option 4. So if you graphed this one, you'd do this like this. Okay, you'd have to go to y equals, then you'd have to go to math, and then down to option 4. And that'll just, it should put the cube root, and then you just put x plus 1. So what you'll find on this is, when we graph this, that the graph is nice and smooth everywhere. Okay, there's no break in that whatsoever. Okay, the idea is what happens when x is -1. If x is -1, you have the cube root of 0, right? And the cube root of 0 is 0. So basically you have -1, 0, and then from there you have positive numbers, and from there you have negative numbers. That's the idea. Okay? What if this problem said this? What if it said 11th root of x plus 1? Would it be any different? No, it's because it's an odd root. Odd roots, basically you can have an odd root of anything, of any number. That's why. Okay? Okay, any questions about that? Okay. All right, let's go ahead and do our break right now. Why don't you come back about 10 after, and we got just a little bit to finish up on here. It's not a... Okay, so on this next page, now this theorem is just kind of going over what we were talking about. You know, if you have constant functions, polynomials, rational, just kind of tells you what we just did. Just sort of a summary of that. The next thing I want to look at is piecewise functions. So I'm going to show you how you can look at the continuity without having to graph, but I want to remind you of a couple of things on this. I want to just have us kind of go over how you would do a graph on this first of all. So we're going to do like a real rough graph. Just draw yourself a little x and y axis. Now the table of values you don't have to do. I want to show you how to do this by hand, and then just one more time remind you of how you can do this on your calculator. So if we were going to graph this, we have x and we have y equals 1 plus x. Now what kind of numbers do I need to use here? Numbers 1 and bigger. Even though that says greater than 1, you need to start with 1, but you know since that's greater than, there will be a bubble there. Now this graph's either going to connect or they're not going to connect. And that's the whole question on whether it's continuous or not at that point. So we're just going to take a couple of numbers that are bigger, okay, 1 and bigger. But we know we have a bubble when we graph 1. Well, we just do this in our head. 1 plus 1 is 2. 2 plus 1 plus 2 is 3. 1 plus 3 is 4, and so forth, like that. Now let's go ahead and let's plot these points, just so that you have kind of a rough graph here. And it's going to go like this. Okay, we're going to have a point 1, 2 with a bubble, and then we're going to have 2, 3, and then 3, 4. So we're going to have a line like that. Okay, that's the graph of the line 1 plus x, but that's when x is bigger than 1. Okay. Now let's go ahead and do the next one. This is the way I recommend you do piecewise functions. Just do tables of values. Okay, and if you do your arithmetic right, you're not going to go wrong. So we have x, and then we have y equals 5 minus x. What kind of, whoa, hold on. I think there's a mistake on that. No, let's see. Yeah, that should be less than or equal to. Sometimes I don't type stuff right. So change that to x less than or equal to 1. Okay, so let's do that. So for less than or equal to 1, we'd use like 1, and then you could use like 0 and -1 and so forth, right? Okay, and we know, would you have a solid dot or a bubble open on the 1? That'd be solid. So I was just making a note to myself. So then we're doing like 5 minus 1 is 4. 5 minus 0 is 5. And then the next one is 5 minus -1. So what is that? 6. Okay. Because subtracting a negative is adding a positive. So if we did this, we'd have a point 1, 4. Okay. Which would be up here like that. And that's now a solid dot. And then 0, 5 would be up there, and so forth. And you just sketch that, okay? Now, in this particular problem, is this thing continuous or discontinuous at 1? It's discontinuous, okay? So the idea is we know we're discontinuous at x equals 1, and we're continuous everywhere else. So if we wrote the interval where we're continuous, we would say what? Negative infinity to what?
To 1.
To 1. Then what? 1 to infinity. You have to say it that way now, okay? And the reason, by having those two parentheses, that's telling you that you're discontinuous at 1. Does that make sense? Okay, no brackets there, okay? So my goal on this problem is you don't have to do graphs. You can if you want to, and it's pretty easy to answer the question if you do a graph, but actually you don't have to do that. So what we're going to do is I'm going to show you how you could just do this. A lot of times you do it in your head. All you really need to do is just plug the 1 in there and in there and see if they're the same. So if you did 1 plus 1, you would get 2. And then if you did 5 minus 1, you would get 4. Okay, since they're different, that's why it's discontinuous. If they were the same, you know what would happen? The graph would connect. Does that make any sense? Okay, either that graph is going to connect or it's not going to connect. If it's disconnected, then you're discontinuous. All right, does that make sense? So you don't have to graph on these things. So the next one, all we're going to do, it's the same thing. Now this, I'm just changing this to 2. All we'd have to do is just do 1 plus 2, and let's see, that's 3, and then we would do 5 minus 2, and that's 3. So what does that mean? What does that tell you? They connect. So is it continuous at 2 or not?
Yeah.
Yeah, absolutely, they connect. So if you drew a graph, you would see 2 lines, but they would connect. There would be no bubble or any break in the graph. So this is discontinuous never. So it would be continuous always from negative infinity to infinity. That's all you got to do. Okay? You just see if the graph connects or not. Okay, so that's all you have to do. The next one, I haven't done this yet. Let's go ahead and do a graph on this one also. So I'll kind of go down the side. You can just draw kind of a little miniature graph. I think you got room to do that. Now let's go ahead and just do 3 tables of values just to make it, or we actually only want 2 tables of values. All right, let's start with x and y equals negative x, okay? Now, the kind of number you're going to use there is numbers that are below 0, because that says less than 0. I'm going to start with 0, but I know that's a bubble, okay? Then I'm just going to take a couple of numbers that are less than 0, like, say, negative 1 and negative 2, okay? So I'm just going to plug in the 0 into negative x. I'll have negative 0 is just 0. What's negative negative 1? And negative negative 2. Okay, so that would be that part of your graph. Okay, and then let's just draw a sketch on these points like this. This is going to go like this. You're going to have 0, 0 that's open, negative 1, 1, negative 2, 2, and then that will take care of the first part of that graph like that. Okay. All right, now let's go ahead and do this part right here. Okay, again, I'm going to do this with a table of values. Okay, we're going to do x and we're going to do y equals x. Okay, we're going to use 0 there again, but is that going to be a bubble or solid? It's still a bubble because it says greater than, right? Okay, so that's still a bubble. And then let's pick some numbers bigger than 0, say like 1 and 2. Well, if you plug it in, you'd just have 0, 1, and 2. Okay, everybody see what I'm doing there? The reason I picked 0 is because I need to know where that thing comes to an end, okay? Don't forget to do that. A lot of times students just jump on to 1. Don't do that, okay? Now plot these points, and then you're going to end up having something like this, okay? Now, this middle piece right here, all that says is if x is 0, then y is 1. Okay, so it just means you have a dot like this. So it just means that you have the point 0, 1 like that. Now that's what the graph of that piecewise function is. This is the graph of negative x. This is the graph of positive x. Then that function value is 1. Tell me if that makes sense what I did. All right, is this thing continuous or discontinuous here? Discontinuous. Okay, there's a break in the graph. So we'd say discontinuous at x equals 1. No, I'm sorry. X equals 0, and then continuous, we'd say negative infinity to what?
0.
And then what?
0 to infinity.
There you go. Good. Okay, like that. Okay? So if you were doing this problem, well, then really all you'd have to do, you could do this in your head. If you plug 0 in for x, don't you just get a 0? You plug 0 in for negative x, don't you just get a 0? So you have 0, 0, and 1. Since they're not all the same, that would tell you it's discontinuous. So you don't have to do that graph. Is that sensible or not? Okay, draw graphs if you need to. Okay, all right, let's work a few of these out. Now these I don't want you to graph. All I want you to do is just take the number and plug it in and see if that is enough to help you understand if it's continuous or not. You can graph if you want to, but it takes time. I do want you to know how to graph stuff like this, but I also want you to just quickly be able to do this. Okay, you can probably do these in your head if you know what you're doing. Okay, it's the same function with just different slight little twists to it that I want to see if you catch. So you plug the number that we got. Now, I think the one that can be a little tricky is number 3 if you're not really paying attention to the problem. Okay, so the first one, if you plug this in, you're just going to do like 1 squared, so you get 1. Then you do 2 times 1, so you get 2. So what's the answer? Is it continuous or discontinuous at that point? Yeah, they're different. Those two things are different, so that means the graphs don't connect. So we'd be discontinuous at x equals 1. That's all you got to do. Okay, continuous, it's everywhere else, so you just say negative infinity to 1, and then 1 to infinity. Make sure you have brackets. That's it. Okay, that's all you do. Okay, is that logical and clear? Okay, what did you get for the next one? Are they the same or different? They're the same. So what's the answer? They're going to be continuous at that point. So you would do 2 squared is 4. Then you would do 2 times 2 is also 4. So that does mean that you are continuous at x equals 2. Okay, there's no break. The two graphs join each other. Okay, so we would say it's never discontinuous. And if it's continuous everywhere, how do you write the interval? Negative infinity to infinity. Good. Okay? All right. So let's do the next one.
Those are brackets or parentheses?
What's that?
And those are brackets or parentheses on the infinity?
They're always parentheses around infinity. Never, ever do a bracket around infinity because it doesn't make any sense. That would be telling you infinity is a point. It's a definite number, and it isn't. Okay? How about the next one? What'd you get?
Discontinuous at 1.
Discontinuous at 1. Okay. So that's 1 to the second is 1, and 2 times 1 is 2 like that. So it's discontinuous at x equals 1. Okay. And that would mean that we would write this negative infinity to 1 and then 1 to infinity. So if you do stuff like that on your homework, you don't have to worry about graphing. It's just see if that one point, see if it causes the graph to connect or not. Okay, everybody with me on that? Okay. Okay. All right, one last thing I want to have you do here is this is sort of an activity. Most of all this stuff is helping you understand functions at a deeper level because we're going to be dealing with functions from here on out pretty much. So what we're going to do is draw a graph, a possible graph based on this information. And essentially I've given you, let's see, 4 pieces of information. Okay, and we're just going to see if we can come up with a rough graph on here. So first thing let's do, just kind of draw yourself like an X and Y axis, and let's see if we can figure out one possibility. Okay, so the first possibility, I give you this piece of information. What does that tell you? If I say f of 0 is 5, what does that tell you? You have a point on the graph, right? What is that point? 0, 5. Okay, so we know we have a point 0, 5. So what do? You just plot that point. Okay, so that gives you what that is. So that's done. Okay, now the next thing is this is going to say the limit of f of x as x goes to 5 is equal to 2. Now remember, we're only looking at possibilities. There's all kinds of possibilities, but let's go out to 5. Okay, and if the limit exists and it's equal to 2, well, what would that mean? It would mean that the right and left-hand limit would both come together, right? And the value of the function right there would have to be 2, right? It'd have to be. Couldn't be anything else. So you're going to have a graph that's kind of the limits approaching, so it's going to do something kind of like that. Okay, so that's what that one tells. Okay, this statement right here, what is this telling you? It's telling you if you go infinitely to the left, what's happening to the graph? It's going infinitely down. So that would mean, well, this has got to connect here, right? It's got to connect, but then it's just saying, and there's all kinds of ways to graph this, it's just saying, okay, as we go further and further to the left, the graph just goes down forever. And that would be one possibility, okay? So that's what that says. All right, now what does this say? This says x is going to the right, and then where's the graph going? It's going up. So you just have to make that turn around and go up like that. That kind of looks like a polynomial, doesn't it? Okay, so that would be that point right there is f of 0 is 5. This is just saying the limit as x approaches 5 was equal to 2, and then the rest of the other two limits are telling you you're going to infinity. Okay, that's a possibility. Does that make sense? Okay, so you just basically want to see if you can take the information and come up with some possibility. It's just an exercise to help you understand functions and statements. Okay, so let's see. Now there's a lot of possibilities on this. This first statement on this one says that g of 3 is undefined. Okay, and there's more than one possibility. You could have a bubble, right? That's one possibility. Another possibility is you could have an asymptote. Okay, but you're definitely not defined at x equals 3. So for now, let's just kind of go out to 3, and we don't know what we have. We may have a bubble, we may have an asymptote. It depends on what the rest of the problem says. Okay, it also says the same thing with f of 10. That's undefined. So let's go all the way out like to 10. So let's see, that's 3, 4, 5, 6, 7, 8, 9, 10. Undefined, that's the same thing. It's either going to be a bubble or it's probably going to be a vertical asymptote. Okay, so that's what those two things are telling us. Okay, now we got these limits. So if you look at this limit, that's saying a two-sided limit as x goes to 3 is going to be approaching 5. Okay, so what that tells me is when you go to 3, the graph is going to have to, from the left and from the right side, it's going to have to do that, right? It's got to come together, agreed? But what would you have there in the middle? Would you have a solid dot or would you have a bubble? You have a bubble. Why would you have a bubble?
It's undefined.
Because it's undefined, okay? So that would tell you that that would be one possibility. The graph's got to connect. The limit's got to approach 5, which it does, okay, but you got a bubble there, okay? All right, is that reasonable? Okay. All right, now the next one, what does this tell you right here, this condition right there?
Approaching 10, it's going to slope downward.
Right, good. And we're approaching the 10 from what side?
From the left.
Okay, that's probably going to tell you you have an asymptote here too. Because remember, we are undefined, so we probably now have an asymptote like this. And exactly, that just means that as we get close to 10 from the left, like you said, the graph does that. Okay, and then these things got to connect somehow. So you'd have something maybe like that. Okay, and then the last statement, what's this telling you? The limit, x goes to negative 10 plus is infinity. What should I tell you? If you're at the right of the asymptote, where's the graph going? It's going up forever like that. So you'd have something like that. Okay, and then what happens beyond that, who knows? Okay, so the idea is I'm just having you give me one possibility. So that graph satisfies every condition in the problem. You're undefined there and there, right? And then you have a limit that's going to 5 around 3. And then you have the left-hand limit around the asymptotes negative infinity, and the right-hand's going to infinity. Okay, does that make sense to everybody? Okay, so again, let's go to this last page. I'll give you a few minutes to just see what you come up with on this. Not everybody's graphs are going to look the same, but you should have the same key ideas with this. Let's see what you can come up with, okay? The same basic ideas. Okay, so when I look at this first example, we have f of negative 5 is negative 4, so you definitely have to have a point there. Okay, that's all you need to do with that. Okay, the next thing is you're undefined, and if it's undefined, it's going to mean you have a bubble or you have an asymptote. That's pretty much it, okay? All right, so this one says you have a two-sided limit And when you approach negative 5, that two-sided limit is going to be equal to 0, okay? So if you have a two-sided limit going into 0 at negative 5, you're going to have something doing something like that, right? But what would you have to have here? You have to have a bubble, right? You'd have to. It's the only thing that you could make any sense out of. Now, so you have a limit both going in at 0 somehow, okay? Then you got to have that like that. That's what this statement and that statement are going to tell you. Does that make sense? Now, you could make the graph connect together in different ways, but you do have to have a bubble there, okay? All right, now the next thing is it says when you go to negative infinity, this statement right here just means if you're going to the left, the graph's going up. So you could have something kind of like that, okay? That's what that says. And then the next statement is going to say that as you go to the right, then you're going up also like that, okay? So the other thing is f of 0 is undefined. So what you're going to have to do is somewhere in here, and it doesn't matter where, you've got to have a bubble there. You have to be undefined there. And then it's going to do something like that. Now there's more than one way you could draw this graph. The key things that I would have to see is I'd have to see that and that, okay? And then I'd have to see that that goes to infinity and that goes to infinity and that's undefined. Now that could also be an asymptote. I mean, you really and truly could draw a graph like this and I couldn't count it against you. So if you had like, you have to have a bubble there, you have to. That thing's got to go to infinity. You got to have the solid there. But you could do something like this. So if anybody did something like this, there wouldn't be a thing wrong with this. I mean, if you did something kind of like that, that's okay. There's all kinds of things. You can even make it go like that. It's just these are the things that you got to show. That, and that. What's in between those is up to you.
Could that be correct?
The only thing that I see wrong with yours is it saying the limit goes to infinity. So as you're going way out here, I got to see that that's going up. Okay, because I'm not seeing any graph past 0. But you got the right idea. Okay, does that make sense? Tell me. Okay, there's more than one possibility, but it's easier if you do this kind of with a matching thing here. Okay, the next one. All right, let's see. So we're undefined at negative 4. We're also undefined at 2. And then the limits should kind of tell you whether you have asymptotes or not. So this is a left-hand limit around negative 4 and a right-hand limit around negative 4. The fact that they're going to infinity is going to tell you without a doubt you have an asymptote there. So you absolutely have to have that, okay? Then the left-hand limit is going to infinity. So you would have to be doing something kind of like that, okay? The right-hand limit around negative 4 would be going, is that also infinity? Yeah. So you'd have to be doing something like that. So you have to have the asymptote, and then the graph has to be doing that. Okay? Whatever you put to the left of that's up to you. You can be creative. Okay? And then this last step just says that as you go infinitely to the right, you're going infinitely down. So way out here, you're doing something like that, kind of an endpoint like that. So I've kind of got that put together, that, and that. The only thing I'm left with is at 2, we're undefined. You could have an asymptote. You could. I don't care. You could also just connect these 2 dots and have like a bubble there if you wanted to like that. That's a possibility. But what I would need to see is you have that, those 3 things. You have to have an asymptote and the thing coming together going like that. You got to somehow show your undefined there, and then you got to show that, okay? But again, there's many possibilities, okay? All right, is there any questions there? Okay, how'd you do? Probably didn't get what I got, but as long as you got the key things, you're okay, all right?